Module 8, problem number 4. The first significant digit in any number must be 1, 2, 3, 4, 5, 6, 7, 8, or 9. Basically, that's saying 10, your first significant digit would be 1. 363, your first significant digit would be 3. It was discovered that first digits do not occur with equal frequency. Probabilities of occurrence to the first digit in a number are shown in the accompanying table. The probability distribution is known as Benford's law. So basically what we're saying is, even though you might think that that first significant digit would have like an equal probability, it actually doesn't. It follows a probability distribution known as Benford's law, and we'll see that when we open up the table to look at the problem. For example, the following distribution represents the first digits in 198 allegedly fraudulent checks written to a bogus company by an employee attempting to embezzle funds from his employer. Complete parts A and B below. So first, let's just take a quick look to see what we're looking at here. So we have two basically data sets or data columns. The first is the distribution based on Benford's law. So you see here we have these probabilities associated with each number. So for example, the probability that 1 is going to be the first digit is 0.301. The probability that 6 is going to be the first digit is 0.067. The probability that 9 is going to be the first digit is 0.046. That's what we would expect based on Benford's law. Here is the distribution of the 198 fraudulent checks, or allegedly fraudulent checks from this employee. So here we have the frequency counts, and what we want to do is check and see if they follow Benford's law. If they follow Benford's law, it's likely that the employee is not embezzling, because that means it's following the expected pattern based on this law. If they don't follow Benford's law, that means it's highly likely that the employee is embezzling, because they're taking checks and that it's disrupting basically the distribution of what we would expect that first significant digit to be. So let's go back to the problem. Using a level of significance alpha equal to 0.05, test whether the first digits in the allegedly fraudulent checks obey Benford's law. What is the null hypothesis? So in our case, the null hypothesis is that they do follow Benford's law, or we assume that they follow Benford's law. So that would be A here. Let's final check. Nice work. What is the alternative hypothesis? The alternative hypothesis is that they do not follow Benford's law. Okay. So let's find the test statistic. Now, going back, remember, Benford's law, we have the probabilities. We don't have the expected count. And the actual fraudulent checks, we have the expected count. So let's go ahead and open this up in StatCrunch and take a look. So as you can see here, here's our probability from Benford's law. Here's the digits associated with the first significant digit, that 1 through 9. And then our frequency from those 198 fraudulent checks. So we need to create another column for that expected count. So what we're going to do is go to Data, Compute, and Expression. We're going to click on Build. So in this case, if you just wanted to do like a simple expression like 5 plus 3, you could just type it in there. But here we want to use one of our columns to calculate this expected count. So first you're going to click on Probability. Again, that's the probability from Benford's law. Click Add Column, and then we're going to multiply that by our number of checks. You can either type using the keyboard, or you can click on here on the calculator. So once you have your expression up here in that top line, probability times 198, we're going to click OK. Then we're going to click Compute. As you see here, it gives you a little message, new column created for probability times 198. If we wanted to, for example, we could even change, we could change in theory, we could change the name of our column to observed and expected if we wanted to help there to make it clearer. So here's our observed checks from the alleged fraudulent check that the employee is embezzling, and here would be the expected counts based on Benford's law. So now let's find our test statistic. Let's go to Stat, Goodness of Fit, chi-square test. Now again, we didn't need to rename our columns there. It just makes it easier when you come over here. So we have observed and expected. Click compute. And here's our chi-square number. So it says to round to 3 decimal places. So that gives us 23.179, but then rounding, we're going to put 80. So let's check that. 23.180. Check answer. Fantastic. So next it asks for our p-value. Our p-value here, again, we're going to round to 3 decimal places, 0.003. 003. Check answer. Fantastic. So using the p-value approach, compare the p-value given alpha equals 0.05 level of significance. Based on the results, do the first digits obey Benford's law? So remember, if the p-value is less than alpha, we reject the null hypothesis. So in this case, we would reject the null hypothesis. Remember, our null hypothesis said that they did follow Benford's law. The alternative said that they do not follow Benford's law. And we said that if they don't follow Benford's law, it's likely, or we would then assume that that employee did embezzle the checks. So in this case, we would reject the null hypothesis because the p-value is less than, see that right here, less than the given alpha level of significance. So check answer. Well done. So what do we say to that? We say that they don't follow Benford's law. We would think that the employee might be guilty. So in that case, we say, yes, the first digits do not obey Benford's law. Check answer. Good job. So that's number 4. If you guys have any questions, let me know on any of the problems.